We're going to start our discussion about cylinders by considering a right circular cylinder. A right circular cylinder is so named because its sides meet the base at a right angle and the base is a circle. We can imagine something that is a circular cylinder that we wouldn't call a right circular cylinder. This would be like an oblong cylinder where the walls do not meet the base at a right angle. We could also consider a cylinder where the base is not circular. But first, let's go back to the idea of this right circular cylinder. And it is made up of essentially lines, a bunch of parallel lines that go through a circle. And if you put together enough of these lines, then you end up with a solid shell that is the cylinder. In the case of the kind of oblique, I think I called it oblong. In the case of the oblique cylinder, we still have lines that go through a circle and they still form the walls, but they don't meet the circle at a right angle. But we say right circular cylinder because there are other types of cylinders. And to help understand what is meant by that, let's look at a definition. A cylinder is a surface that consists of parallel lines through a plane curve. In the case of a right circular cylinder, the plane curve is a circle, and of course the parallel lines I was just talking about make up the walls of the cylinder. The plane curve, though, can be any number of curves, and it might be helpful to think sheets. As in, we can imagine a right circular cylinder being constructed out of a sheet of paper by joining the edges together and taping it or something. Before I get too far off topic, though, let's look at an example. Let's graph y equals z squared. Let's start with the plane curve, and in this case, it's going to be the trace in the YZ plane. In the YZ plane, we have a parabola that's going to open in the positive y direction and is symmetric with respect to the y-axis. We want to translate that into 3 space. Now what I'd like to do is reproduce this parabola in the YZ plane, but I'm going to put it in space, R3. So there's our parabola. Now I need to give it some edges. And the edges are going to be lines that are parallel to the x-axis. And then I need to, you know what, I'm going to copy and paste this. I feel like it's kind of cheating, but I need to give you a good representation. There. And then we need to close off the back of it. So I'm going to give it another line back here. There, that'll work. And what we've now got is some parallel lines that are going through a plane curve, that plane curve being the parabola in the YZ plane. And that meets, well, this is starting to meet the definition, a surface that consists of parallel lines through a plane curve. Let me draw a few more of them. And then what'll help sell it is if I give it some grid lines across the top. And then kind of interior to the parabola. It's kind of like we're drawing a wave. Now, what can help sell this for me is if I strengthen the edges of it. If I draw them kind of thicker, it helps. Now, at this point, what I've got is this is a parabolic cylinder, and it exists only on the positive x-axis, because when I drew all this, I didn't draw anything behind the x-axis. And so just to fix that little issue there, I've moved the y and the z axes. That'll just help sell the illusion a little bit more. I mean, that's what we're doing. We're creating an optical illusion here. Now, aside from the fact that we're told there are parallel lines through a plane curve, you may wonder, why does this go all the way along the x-axis? It doesn't have x in the equation. I'd like to remind you that in R2, if we consider the equation, say, y equals 4, then that's a horizontal line at the value of y equals 4, and x doesn't appear in the equation, but our x-coordinates take on all of the real numbers on the x-axis. Same idea here. So if a variable is missing from an equation, then you know it takes on every value for that variable. Well, that was such a fun challenge. Let's do another one. We're going to graph z equals the sine of x. Now we can consider the trace, this time in the xz plane. And the trace in the xz plane is a normal looking sine curve. And now we're going to try to translate that, and we're going to succeed in translating that into R3. So I'm going to draw this sine curve. And there we are. Now I need to give it some parallel lines. This time these lines are going to be parallel to the y-axis. Now I've kind of gotten some help from my iPad app here, but if you were using a straight edge, you would want to make all of these segments the same length. And then in order to help my eye believe what I'm going to draw, I've tried to put the midpoint of each of these segments to be touching the peaks and the troughs of the sine curve. And then I'm now going to just redraw that sine curve using these parallel lines as my guide. I forgot where I was aiming for there. There. And then one more. Boy, that one really gave me it was confusing, that last one. And then what I'd like to do is give it some contour lines. Helps sell the illusion a little bit. And then bring these down, contour lines that way. And then I'm going to go with the parallel lines. And these are the parallel lines that essentially make the curve. They are through the plane curve. The plane curve, we may have kind of lost it here, but the plane curve over here is the sine curve, as you can see. And that particular sine curve exists within our shape. And all those parallel lines are going through that plane curve. And this is what I meant when I said think sheets. You can imagine this being created out of a piece of paper. Looks like I missed a couple of contour lines there. So this is what we're aiming for in your work for this section when you're drawing cylinders. And as I said before, it can kind of help if you thicken up the edges a bit. There we go. Now I've seen work from previous students. You're probably going to draw better than I will, and that's totally fine. I want you to give it your best shot if you are not artistically inclined. Just give me something that looks reasonably like what it's supposed to look like.